Greetings everyone. Our group is presenting our project for the mechanism sessional tutorial 5. Our work involves the detailed kinematic synthesis and simulation of a windscreen wiper linkage system. I would like to quickly introduce the team members who contributed to this analysis. Myself, Aditya Prakash Gupta, Soham Mukherjee, Ishan Bala and Anupam Kumar. We begin with a complex design task, converting continuous motor rotation into the precise oscillating sweep of a windshield wiper. This challenge formed the basis of our project. Our objective was to model and simulate a linkage mechanism capable of this specific motion, focusing on two critical goals. First, to accurately generate the complete wiped region on the glass. Second, to ensure the mechanism strictly satisfies a quick no return kinematic condition, which is why is that no quick return crucial. In this context, it means the time for the forward wiping stroke must be exactly the same as the time for the return stroke. This ensures the smooth, steady motion essential for driver visibility and safety, unlike the industrial mechanisms that often employ a fast return stroke. To validate our model, we followed a clear approach which structures our presentation. We first define the mechanism's configuration and geometry. Next, we apply the essential theoretical concepts followed by the steps of our synthesis process. We conclude with a potential innovation for the design. So, this schematic shows the specific geometry and the link lengths we analyzed in our model. The input crank OA is 30 mm, the primary coupler AB is 200 mm, and the driver rocker OAB is 80 mm. The final wiper arm assembly links DO6 and CO4 are both 300 mm long. These dimensions define the system's kinematic performance.
Greetings everyone. My name is Soham Mukherjee, and let's begin by grounding our understanding in fundamental kinematics. The core of any complex mechanism, including our Viper system, often relies on the four-bar linkage. It is the most simplest and most widely used closed chain movable mechanism. As shown on the slide, a four-bar mechanism consists of four rigid links connected in a loop by four revolute or pen joints. In this case, we call it a 4R mechanism or a RRRR mechanism. Each link in the 4R mechanism has a specific role. The frame or the ground is the fixed link. The links attached to the frame are the ground links. One acts as the input link and the other acts as the output link. The final link is the coupler, which transmits motion between the input and the output. In our overall 6-bar Viper mechanism, the primary driving assembly is an initial 4-bar linkage. It takes the continuous rotation from the motor and converts it into the necessary basic oscillation that drives the rest of the mechanism, making its kinematic behavior critical. Moving on, we first need to know what is the Grashof criterion. To understand and predict the motion of this initial 4-bar drive, we rely on this criterion. This criterion is an algebraic relationship that uses only the lengths of the four links to determine the relative motion capabilities. The primary question it answers is, will at least one link be able to completely make a 360-degree revolution? The rule is simple. We designate the shortest link as S, the longest as L, and the other two as P and Q. A full rotation is possible if the sum of the shortest and longest links is less than or equal to the sum of the other two, that is, S plus L less than equals to P plus Q. Mechanisms that satisfy this are called Grashof mechanisms. The type of motion the mechanism exhibits does depend on where the shortest link is placed. Case 1. The crank rocker. This is what we require for the input stage of our Viper. If the shortest link is adjacent to the ground, we get a crank rocker. This means the shortest link can fully rotate, that is crank, while the link attached to it can only oscillate, that is the rocker. Case 2, the double crank. If the shortest link is the ground, both grounded links can rotate fully. This is also known as the drag link mechanism. And case 3, if the shortest link is the coupler, neither grounded link can perform a full rotation, they can only oscillate. By applying the Grashof criterion to our initial 4-bar drive, where the input link is the shortest link and adjacent to the ground, we can ensure it functions as a crank rocker. This fundamental motion is essential for the continuous symmetric oscillation achieved by the final 6-bar Viper assembly.
Hello, I am Anupam Kumar. I will discuss the synthesis and modeling for this windscreen wiper mechanism. Our main objective was to create a mechanism that transforms rotary motion at the input pivot into a controlled wiping motion at the blade tip. The challenge was to cover the full arc of the windshield using only revolute joints for a reliable, low maintenance design. To start, we fixed the link lengths and geometry. This included critical dimensions such as the position of our pivots and the lengths of our input, coupler, and output links. With this set, we used a graphical kinematic approach. This meant plotting the input link's successive positions and tracing how the linkage moves, constructing the exact coupler and output points at each step. Once the linkage was defined, we traced the path of the wiper blade tip as the crank rotated. This allowed us to visually map out the effective wipe region across the windshield. Using these plots, we checked that the swept area made the required coverage, ensuring no quick return effect and a smooth, continuous motion. This synthesis process ensures the linkage is not just theoretically sound but functionally practical as confirmed by digital simulation. The end result is a simple and efficient 4-bar wiper system that delivers complete arc coverage with minimal complexity, ideal for real-world automotive use.
Here, as we can see, our 6-bar linkage in action, converting the continuous 360-degree crank rotation into the necessary smooth oscillatory wipe. Hello everyone, I'm Ishan. We now move to the kinematic simulation, the crucial final step validating our mechanism's performance. Our simulation confirms we meet two key design objectives: windshield coverage and the quick no return kinematic constraint. First, wiped region confirmation. As you see from the path traced by the wiper tip, the swept area confirms our link length successfully achieved the required coverage. Second, the no quick return condition. This is vital for uniform cleaning, meaning the forward and return strokes must take equal time. Our 6-bar design was specifically engineered for this symmetric oscillation. The simulation shows this consistent equal time movement, confirming we have strictly met the no quick return condition. Next, we move on to the innovation slide. Beyond our core synthesis, we also explored two potential innovations. First, an orientation adaptive wiper blade. The concept is for the wiper to rotate, becoming horizontal at the bottom of his path. This could be done with a secondary link or cam, enhancing corner reach and widening coverage without needing a longer arm. Our second concept is smart variable amplitude sweep. This is a sensor control system that would adjust the wiper's swing amplitude based on rain intensity. A full sweep for heavy rain or a narrower, more efficient sweep for lighter rain. These concepts show a clear path forward, moving from a reliable kinematic solution to an intelligent adaptive system. Thank you.